So now that we're finally essentially done with everything that we need to know about limits and continuity in Calculus 1, I thought it would be fun to actually look at the formal definition of a limit and the formal definition of continuity in terms of epsilon and delta. This is what we refer to as the Epsilon-Delta definition. And this is definitely something outside the scope of Calculus 1, so if you're solely focused on your IB or your AP Calculus exams, then you don't really need to watch this video, but if you're interested, then I do recommend watching it, because it is actually quite an interesting topic that will definitely appear if you study math and you take a real analysis course, which ideally comes after vector calculus. And so essentially, we can make the statement that the limit as x approaches a of f of x equals to L, and of course L has to exist, if and only if, for all epsilon greater than 0, if we ever take a number epsilon that's greater than 0, then there must exist a delta that's greater than 0, such that whenever x minus a, whenever kind of the absolute value of x minus a, or the distance between x and a, is strictly less than delta, then the distance, or the absolute value of f of x and our limit L is less than our kind of pre-selected epsilon. So we chose an epsilon. Epsilon and delta are just Greek letters, by the way. So we select an epsilon greater than 0, and we can essentially, then we should be able to find a delta that as long as x is within delta of a, then our function is going to be within epsilon of our limit. So that kind of is a bit weird to state, but let me show you what I mean by that. So I drew out this arbitrary function, f of x, and here we have our a value, here we have our limit L, and essentially, let's suppose that we pick some arbitrary epsilon greater than 0, and we can consider epsilon plus L, or sorry, L plus epsilon and L minus epsilon right over here. So this is L plus epsilon, L minus epsilon. And essentially what that's going to do is that's going to define a kind of neighborhood, and this is what we call the epsilon neighborhood. It defines an epsilon neighborhood around our limit L. So we have this epsilon neighborhood around L, and essentially what we're saying is that the limit of this function, f of x, is truly equal to L if and only if, for whatever epsilon we select, we're able to define what we call a delta neighborhood. This right over here is what we call a delta neighborhood around our a value, such that whenever our x value is within delta of a, so whenever the distance between x and a is less than delta, so whenever x is somewhere contained within this delta neighborhood of a, then the distance between our function and L is located somewhere less than epsilon. So essentially, like let's suppose we pick this x value right over here. This is located within the delta neighborhood of a. Then our f of x value is going to be somewhere within this epsilon neighborhood, and that holds true for this particular point we selected. So essentially what we're saying is that we can always define a delta neighborhood around a such that if x is located within this delta neighborhood, then the distance between our function and our limit is going to be located within the epsilon neighborhood. So that sounds a little bit weird, but I'm going to try to give you an example of why we'd actually use this definition, because it seems very convoluted and not something you would use very often, although it does certainly appear quite a bit in real analysis. So let me take this purple color. So what we're going to do is we're going to try to prove that the limit as x approaches 3 of 2x plus 1 equals 7 using epsilon delta definition, because I enjoy torturing you. And so essentially, what we're going to do over here is we're going to try to take this inequality over here, and this one over here, this inequality of f of x minus L, or the absolute value of f of x minus L is less than epsilon, and we're going to try to take this and construct this inequality over here, or this absolute value over here. The absolute value of x minus a is less than delta. And by doing so, we'll be able to kind of construct delta as a function of epsilon. And so let me show you what I mean by that. So what we can do is we can say, let's suppose right over here that epsilon is greater than 0, right? We don't really care what this epsilon is. We're just going to keep it arbitrary. We're going to keep it kind of as a variable. And so then we're going to say choose some delta, and we don't really know what this delta is going to be equal to, so I'm just going to say delta equals blank, because we don't really know what this delta is just yet, and we're going to try to find that delta in a moment, such that whenever the distance between x and a, And in this case, what's our a value? Well, our a value is 3, right? So whenever the absolute value of x minus 3 is less than delta, then the distance between our function, what's our function in this case? Our function is 2x plus 1. So 2x plus 1 minus our limit. What's our limit value? Our limit value is 7 in this case. 2x plus 1 minus 7 is less than epsilon. And so let's see how we can use this inequality or this absolute value to get this one over here. And so what we're going to do is let's first of all just see how we can manipulate this a little bit. So 2x plus 1 minus 7, we can write that as 2x minus 6, and that is going to be less than epsilon. And then what can we do? We can factor out a 2, right? And so we'll get the absolute value of 2 times x minus 3, that looks a bit weird, is less than epsilon. And then we can go ahead and divide everything by 2. We can think of like taking the 2 out of the absolute value. And so we'll get the absolute value of x minus 3 has to be less than epsilon over 2. And so essentially what we're saying here is whenever the distance between x and 3 is less than delta, we can define delta. And in this case, we can define delta to be equal to epsilon over 2, right? And so essentially, we came up to this point in the inequality where we got that the distance between x and 3 is less than epsilon over 2. However, we also know that the distance between x and 3 has to be less than delta. And so we can just say, okay, suppose that suppose that delta is equal to epsilon over 2. If we pick delta to be equal to epsilon over 2, right, then regardless of whatever epsilon neighborhood we define around our limit value, then this equality, then this inequality over here is always going to hold as long as we pick delta to be equal to epsilon over 2. So what that means is that if we choose any epsilon neighborhood around our limit L, in this case our limit is positive 7, if we pick any epsilon neighborhood around positive 7, then as long as we define our delta to be equal to epsilon over 2, then we will always have a valid delta neighborhood around x equals 3. And so essentially we're able to say that the proof is complete. So we put like this little box thing over here and we can shade it in if you would like. And so essentially we're able to kind of pick some delta, and this is a valid delta right over here. It's defined in terms of epsilon, it's independent of x, it's independent of the a value you select. And so we're able to essentially say that as long as we pick this to be our delta value, then we have a valid delta neighborhood with respect to our epsilon neighborhood. So this might seem a little bit odd at first, but take a moment to think about this a little bit, and I encourage you to kind of go over a couple of examples to see how we can actually use the epsilon delta definition of a limit to prove these seemingly quite simple limits over here.